It's a great pleasure to tell you about the Juno mission to Jupiter. This is actually a talk that I gave at the AAS.
Is that too dark?
And in Alaska last year, and because you had to do it all, they insist that you transmit your talks over the line, and this is a really large talk with a lot of movies. It crashed in the middle of the talk, so I'm praying that everything will go fine here. I'm going to tell you about the Juno mission that was launched last year and is on its way to Jupiter. And I've got this sort of little tadpole thing here on the front page because I also hope to tell you a bit about how we think the giant magnetosphere of Jupiter is more like a comet than it is the terrestrial magnetosphere. So give you some magnetospheric physics at that point. Okay. So let's talk a bit about Jupiter. We know that the giant planet has these beautiful cloud structures, these belts and zones, and Cassini has shown us that we have these beautiful patterns of east and west belts and zones, and we have the great red spot that's been observed since the era of Galileo, and more or less the same sort of place moving around. And we have some sense of what it's like on the outside. We look at the cloud structure, we see these spots come and go, the belts and zones changing a little bit, but pretty much weather is pretty constant on Jupiter. We were able to take these cloud pictures and turn them into a polar projection. And this is interesting. You can see these zonal winds, and I think if you look carefully, you can see these belts alternating belts and zones going quite close towards the pole. Obviously, since we were confined to the equator with our current missions, we haven't been able to look at the poles, but those of you interested in rotating fluid dynamics will see, aha, cylindrical flows perhaps projecting down inside. But we don't know what it's like inside. We have looked at the clouds spectroscopically, and we have a sense of what we were expecting when we sent the Galileo probe into the atmosphere back in 1995, and we thought there were going to be 3 layers of clouds. We thought there'd be ammonia on top, ammonia ice, those are the white clouds, and then ammonia hydrosulfide is we think what happens is that with UV light on that sulfurous cloud, you end up with this brown tinging. So we think the brown on Jupiter's clouds are in fact sulfurous compounds. And then underneath that, we expect there to be a whole load of water, deep water clouds. Now, of course, what happened when we went there, it was completely different, as tends to be the case. And what we saw, there was very little water, very few clouds. So what happened? Well, we sent the probe, it turns out, into this dark region here between a belt and zone region, into what turned out to be a hotspot. We know it was a hotspot because the infrared IRTF telescope on the ground looked at the hotspot, and the impact was somewhere in there where it's hot, looking down between the clouds into a descending hot zone, just like the Chinooks that come off the mountains here in the spring, bringing in this warm air. And so we think what happened is we went into a odd warm spot. Now, this is important because when you look at the abundance of elements here relative to the sun, this seems to have died. Nope, there it goes. Look at the elements relative to the sun. What we see is that most of the elements seem to be enhanced by about a factor of 3. There is, in fact, some rain out of these noble elements, helium and neon. But if we look at the sort of what astronomers would call heavy elements, metals, but in fact, these are the rock building elements, and water, ammonia, methane that produce our oxygen. We're related to the abundance of oxygen, nitrogen, and carbon. You'll see everything is enhanced by about a factor of 3 except for the water. So the water was missing, which tells us that oxygen is missing. Now, of course, this is very important because oxygen is the 3rd most abundant element, and we would expect there to be a lot of it there. Furthermore, our theories of how the gas giants formed is condensation of an ice core beyond the frost line, somewhere between Mars and Jupiter, onto which the hydrogen was pulled in. So if we're missing the water, we don't know the amount of oxygen in the solar system. We don't know how the gas giants formed. So it's key to know the amount of water in Jupiter. So this was the objective of Juno, which is on its way to Jupiter. And the goals here is to really understand the interior and how this affects our ideas of the origin. And since it happens to be flying over the poles, we can also do some magnetospheric science, which was my primary interest. This is a NASA New Frontiers mission, so it's $1 billion class. That's a cafe latte per person per year for 5 years, for those of you who want to justify it to your neighbors. It's PI-led, with Scott Bolton, the PI, being from Southwest Research. And we were successfully competed with others to have this mission selected and funded by NASA, funded by the taxpayer, of course. It is unique. It's a solar power. I'll show you the solar panels. We have 8 science instruments. It was launched in 2011, and we'll get there in 2016. Now, the clever thing is that we have to avoid the radiation belts. The very close-in synchrotron belts are very hazardous to spacecraft, sensitive electronics that get zapped. So what we're doing is we're flying over the poles and skimming over the clouds and underneath the radiation regions, and we will have a 11-day period, so orbits that go up quite far out, that allows us to send the data back, and then we come back in again and fly over the poles. So we're planning for 32 science orbits, a total of 34 passes of the planet, and then what happens is we process the spacecraft as we go to, this is orbit 1, 16, and 30. The orbit processes because of the oblateness of the planet, and then sooner or later we will have to go through the radiation belts, and we expect to have damage to the spacecraft then. So one of the key ways to avoid, protect the sensitive electronics is to put all of the most sensitive stuff into a vault with a thick titanium layer around the outside inside a box, and so we have a vault that protects a lot of the instruments. We have solar panels. These were folded up, and you can sense the scale with these humans here. This is actually problems getting this pointer to work. Yep. Do you think we could? They have unfolded. I'm sorry, but do you think you could? It's not critical. Okay. They have unfolded. We know that because they're working now in space. You can see we have the magnetometer on the sort of triangular end piece there on one of the 3 wings. Here you can see for scale, the bottom left is a human. And you can see these are large. So the whole diameter of the spacecraft is about 66 feet, right? So they're really, one of these solar panels would maybe just about fit in this room. And there's 3 of these which provide about 300 watts power when we're at Jupiter. Then we have various, thank you. Then we have various instruments on here. We have a magnetometer, inboard and outboard here. We have various energetic particle instruments, JEDI and JADE. Gravity science is going to be done with the radio antenna. I'll show how that works in a minute. And then we have a couple of cameras. We have a UV spectrometer and an infrared spectrometer, and then a little thing called Juno Cam, which is our only real camera, and that's the EPO experiment. And then finally we have antennas for measuring radio and plasma waves. Now the advantage of, this is a spinning spacecraft, which has a huge advantage for particles and fields, but not very good for cameras. It's it's unlike the other big planetary missions where everything's being, whole missions talked around taking the best pictures you can with the cameras. On this team, the cameras just get pointed wherever they end up, and actually the particles and fields rule this mission. Okay, those of you involved maybe with missions like Cassini, we have to deal with very temperamental PIs who run the cameras and tell us what we have to do. Not this case. Okay, little cultural reference. So the nice thing is that we're going to design our mission to fly past Jupiter and map out the interior. So we have successive orbits that come by several degrees in longitude apart, and so over a series of sequence of flybys we begin to fill up a map of various things: the gravity, the magnetic field, and the interior. So we're using the same sort of technique that's done for measuring the gravity on the Earth and the Moon and other planets. We'll map out and describe in terms of spherical harmonics the perturbations to the gravity field by distributions of mass inside. And the way we do this is by comparing the signal transmitted and the signal received, and looking at the Doppler shift due to the fact that as the spacecraft moves past the planet, its orbit will be wiggled a little bit, moving forward and away from the Earth a little bit, and measuring that Doppler shift will be able to tell us the distribution of mass over which the spacecraft is flying. We then, of course, turn all this into spherical harmonics and get some sense of power as a function of harmonic degree, and we hope to be able to improve, moving up to maybe degrees of 8 or maybe even 20 or so, to get some sense of the internal structure, depending to some extent on where the mass is and how it's distributed, how much detail we'll be able to get, but considerably better than the current knowledge, which is sort of these numbers up here. So that'll be useful for getting a sense of the interior distribution of mass and the winds inside. Now the problem is that to understand the interior and interpret this distribution of mass in terms of internal structure, you need an equation of state. And this is actually something that is a lot of work on, a lot of debates about how hydrogen with a mixture of helium works under different pressures and temperatures. And so there's a lot of experiments, but the experiments don't go very deep into the pressures that we expect to see. So if you look at the current, this is from Tristan Guillot's review chapter in the Jupiter book, this is the sort of current idea of what we expect. We expect the dynamo layer to be extending out to about 80% of the radius, but our knowledge of the sort of these pressures are sort of 2 megabar pressures. Now once you get down to that sort of pressure, hydrogen turns into a metallic state where the electrons and the ions can move and the protons can move separately, and this is where we believe the dynamo is generated in this region that extends out to about 80% of the radius. This is much larger than the dynamo regions in any of the other planets, hence the really strong field on Jupiter. But we're trying to understand what it's like inside. We are dependent on the equation of state, and it's a good question whether or not when we actually get there and start making the measurements, how good the equation of state will be. And I suspect we'll take the measurements, and as the equation of state improves, our knowledge will improve on how to use those data and apply them.
Could you comment upon what is the greatest uncertainty in that previous slide?
This one here? Yes. The greatest uncertainty? You mean how much helium is... Well, I think one of the big uncertainties and the biggest debate is the issue of the core. Is there a separate core of iron and rocks? We think there's about 15 to 20 Earth masses of rock-like material, and that's from the abundance of elements. But the question is whether or not it is a separate core or whether it's mixed in the lower layers. And the recent work that's been done by Berkeley scientist Militzer, I think is his name, has been working on how you would probably have a mixture of these elements, these metals, in with the hydrogen, the metallic hydrogen, rather than having them separate. So there's a whole question about whether there is a separate core here or whether it's all mixed in. There's also some issue of where this plasma transition occurs, so how far out the dynamo would be. And then the third issue is the issue of how much of the helium, when you have a relatively cold hydrogen mixed with helium, the helium tends to rain out. And we know this is very much the case at Saturn, which is a much colder planet, and the helium has rained out from the atmosphere down towards the metallic region. So quite a bit of questions about the composition, the chemical composition, and of course that's going to affect the equation of state and hence the dynamics of what's going on in the interior. The source of heat in the interior is thought to be very much the heat of formation, making a big giant planet 320 times the mass of the Earth, ends up with a lot of gravitational potential energy converted into heat in the interior, differentiation of denser material on the interior, lighter material on the outside leads to a lot of heat. And so Jupiter, like Saturn and Neptune, emits 2.5 times the amount of heat that it gets from the sun. So this is very much an internal heat, not nuclear driven like the sun, but just heat of formation, residual heat of formation. So lots of questions about how this actually all works in practice. So one of the things that we want to know, and we hope we might get from looking at the flow field inside, is to help put some, try and understand the dynamo at Jupiter. And of course we wanted to measure the magnetic field. In order to do that, we have some sense that the original idea, I guess originally going back to Busa, was that there would be these cylindrical flows inside, but it may be that instead of cylindrical flows there could be a lot more turbulence and much more less cylindrical, more turbulent flow on the inside. We don't know the relative importance of rotation over the turbulence inside. So that's one issue. And so the idea is that we can constrain the dynamo by measuring the magnetic field to considerable more detail than presently. So the usual story is, again, to show power as a function of harmonic degree. And here we have the Earth's magnetic field as it is described in detail by spacecraft and ground-based measurements. And you'll see that we can describe the field from the interior quite well, up to about, I think that's about 12, 14 in degree. But then we have crustal magnetization, which affects the higher order moments, and so we can't describe the dynamo to these high degrees. Now the situation of Jupiter of course will be very different, because we don't have a crust. We'll be able to measure the dynamo to very high degree, and so these two lines here are hypothetical descriptions of what if we had a dynamo that goes to 75 times the radius, or versus 85% of the radius. You would expect to get different distributions of these harmonic degrees. Actually, I suspect we haven't a clue really how the dynamo is on Jupiter, and it'll be useful to see what we get and whether or not it comes anywhere close to these predictions. So the dynamo is a big goal of the mission. But the primary goal, or the one that is perhaps important for origins and evolution of the whole planet, is the issue of where is the water, and to some extent what drives the winds. But these are the atmospheric goals, and the way we're going to do this is a very clever way. We're going to use microwaves. So everyone knows that water absorbs microwaves. That's how you heat up your tea. But instead of generating the microwaves, what we're doing is we're using the microwaves that come from the deep interior and come out through passing through the water clouds, ammonia clouds, and then we'll measure them at 6 different wavelengths, and this will allow us to map out the distribution. So we have these 6 different antennas at different frequencies that will measure microwaves coming out from the interior, and then we expect, as we fly over, to measure the amount at these different frequencies, which will give us a sense of the amount that's coming from the interior. And then as we go over the planet, we should expect to be able to map out the amount of water by looking at the different frequencies as we go over the bands, the belts and zones, to see how much there is there. So this will give us a sense of mapping the amount of water that's in the interior. Yes? Okay, so we are going to have to use modeling techniques. I mean, you have to invert this. You're basically trying to do a CAT scan. And so you're going to have to model water as a function of depth, water and ammonia, because they both absorbed at these different frequencies, and then invert your observations to derive distributions in space. So it'll give you, it should give us absolute quantities, at least of the amount that's in these layers. Now there could be some more oxygen deeper down, but most models of the interior have most of the water in the outer layers rather than having any down deep in the core. I mean, you could imagine that there may be some in the rocks deep down in the core, but that's relatively small compared with this layers on the outside. Yeah. Thermal emission from the interior, right. The microwaves? Yeah. Yeah. Where's the photosphere? Yeah, good question. Yeah, that's a. Well, there was this sketch. This one. I'm gonna have to go back and then go. Let's see if I can do this. Now that you're gonna make me crash my computer, I know you are. Okay, here we go. I think there was a sketch. See if it has numbers. I think it may have numbers. It's going to come any minute, don't worry. Okay, so now, let's see. There's going to be a plot on the right. Have we got a scale there? Temperature. Oh yeah, it's got pressure. This is a schematic, so don't get taken too serious. But it's sort of, we're expecting it mostly to come from the tens of bars, 10 to 100 bar. So I'd call that would be the effective photosphere for these emissions.
Roughly
how deep is that? It's still relatively, yes, that's still relatively close. On that pie chart, it's right up near the top. Yeah. So no, they're not going to, the microwaves aren't going to tell us about the deep interior. That's going to have to come from the gravity and the magnetic field. So I actually don't think we're going to determine whether or not there's a core. It's going to be really difficult to do that with the measurements that we have. I think we're going to be very dependent on the models, and I have a feeling we won't be able to say for certainty. I think that's a tough measurement, and I'm not really sure how one would be able to do that. I'm sorry? Seismology. Yeah, so I think there's been some attempts to do the equivalent of helioseismology on Jupiter, and I'm not sure that they've got any results yet. Maybe you can. Did you have some results? Okay, good. It's okay. We should talk after. That sounds interesting. I'd heard that they hadn't detected it, but it's good. L = 1 is a start. Good. So let's talk about the magnetosphere. So we have this giant magnetosphere, very strong magnetic field, leads to a volume that is huge compared with the size of the Earth's magnetosphere. All of the Earth's magnetosphere would basically fit within the planet. And we have a magnetosphere that extends for well over 100 times the size of Jupiter in away from the planet. So it's a very large volume. It extends well beyond all of the Galilean moons, and indeed Io, the innermost Galilean moon, produces about a ton a second of material, sulfur and oxygen, becomes ionized and trapped in this magnetic field. Jupiter rotates every 10 hours, so coupling to this rapidly rotating planet provides a lot of energy to the plasma, heats up the plasma, gets its energy from the rotational energy of the planet, but also means that the magnetosphere is dominated by rotation, and the plasma is flung out along the field lines to the equatorial regions. So we have an equatorial plasma sheet dominating the location of the plasma. But we haven't explored the poles. We haven't been over the poles, so we don't really know what's up there. In the equator, we have this moon Io that drives strong electrical currents between Io as it moves through the plasma. We have all sorts of processes happening locally around Io as the plasma flows by, ionizing the atmosphere and stripping off the outer layers of the atmosphere. Lots of chemical reactions, charge exchange, ionization happening on around Io. But the net result is a very large donut of charged plasma surrounding Jupiter that emits about 2 terawatts of UV emission. We can observe this. In fact, the Cassini mission, as it flew by, the UV instrument PI'd by Larry Esposito here at CU, made measurements of this torus and the emissions, and we were able to make all sort of useful diagnostic measurements of the composition and energy flow through this region. So we know it lasts for about 20 to 50 days before it eventually moves out into the vast magnetosphere. One of the big clues for what's going on in the magnetosphere is to look at the aurora, just as with the Earth and other planets. And the Hubble Space Telescope has taken a bunch of really spectacular series of images of the aurora. And I'm going to show you here some of the raw data from, somewhat cleaned up by John Clark and his team, of the aurora at Jupiter, looking at the north and south poles. The 10-degree tilt of the magnetic field means that you tend to look at the aurora when that magnetic pole is pointed towards you, and so they alternate between north and south. But there are various features that you can begin to recognize and see. First of all, you can see a sort of fairly steady auroral oval, and if you're used to looking at the Earth's auroral oval, don't think open closed boundary. This is in fact a separate oval related to the interior dynamics of the magnetosphere. You'll also see some activity in the center of this dipole, of this auroral oval, and we'll talk a lot about that in a bit. And then the third type of aurora you can see is, you may see a little line and streak, and that is Io, particularly Io, and a wake of plasma behind it.